Hi, today we'll speak about unstated Kalman filter and its implementation for pedestrian detection or vehicle detection in self-driving cars. Speaking about self-driving cars, we have two types of sensors, Lidar and RADAR, and we will use these measurements from both of sensors, fuse them using unstated Kalman filter in order to estimate the XY position of a moving object or a pedestrian and its velocity components. I will not explain UKF and why we need it because I think I will give a link below in the description for that. But first, let's speak about our simulation environment. This simulator is built by Udacity for self-driving car diploma. And by the way, it's open sourced and you can download it from a link below in the description. Okay, so if we try the simulator, we can find that this is the initial position of a moving object. In this case, this blue car. And here my sensors are located. So when the car starts to move like that, I will get bunch of measurements from Lidar and RADAR. The location of these sensors, as I told you before, is here, and the car is moving around. This situation similar to the situation when we are about to move with our cars and we start to look around. Are there children or not? Are there bicycles or not? Other cars or not? Some obstacles or not? So let's have a look at these measurements, and we can see here there are two types of circles, red ones and yellow ones. The red ones are the measurement from Lidar, and they are the XY coordinates of a moving object, of our cars in this case. And the blue ones are the measurement from radar. And as we see, it's a blue circle with an arrow. Why? The answer is because the radar measures range, bearing, and range rate. So this arrow refers to bearing. Bearing, in this case, is angle between uh, motion vector of the moving object of this car and the x vector of our sensors. As we see that these measurements are noisy and we need to fuse both of these measurements in order to get a good estimate. We will use uncentric Kalman filter. First, because this dynamic is nonlinear dynamics. That's why we can't use ordinary Kalman filter, and extended Kalman filter will not give good results. So let's see how we will use unstatic Kalman filter. For using any Kalman filter, either Kalman filter or extended Kalman filter or unstatic Kalman filter, we need a dynamic motion. In this picture, as you see, we have here our dynamic motion. The state x time k plus 1 can be evaluated using these terms. Here we have two terms. This is the dynamic motion, and this is the additive noise. And here is supposed to have two types of noise. Noise from velocity sensor or acceleration, because we consider that it's a constant rate velocity model. So we deal with our velocity as if it's a constant. So any changing due to acceleration, it will be considered as if it's noise. And also we have a constant rate. So any change in angular rate, uh, we will deal with it as if it's noise. From this dynamic model, we can see that here is a velocity divided by the angular rate. In the case of zero angular rate, it means that we have a straight motion. It will cause a problem because we divide in zero. So before applying this dynamic model, we should check if we have a straight line motion or not. If we have a straight line motion, so we will deal with it as if we have ordinary straight line motion without any rotation, and we will use motion models and motion equations in order to estimate uh, the transitional state vector. Okay, so this is for prediction. For measurement, we have two types of measurements. So we need observation model or measurement model for radar and lidar. For radar, as I told you in the beginning of this video, radar measures three quantities: range, bearing, and range rate. And they are evaluated according to these equations. And as we see, these equations are functions of our state vector. It's not a linear function. For lidar, measurement model is similar because lidar directly measures x and y coordinates of the moving objects. Okay, so now let's have a look at the code. Udacity provided us with the simulator and a code, a piece of code that connected the simulator to our program. This simulator is considered as a server that sends some JSON, some data in JSON format, and our code is something like client that receives this JSON format and extract from them the useful information. What's important for us is that we get measurements from lidar and radar, and we will use them in order to get a good estimate to car trajectory or to pedestrian trajectory. Uh, this is the UKF class, and here I can find some arguments and some functions or methods to be written. A link to my GitHub repository will be provided in the description, where you can find this code and you can read it. But now let's try this code. So I'll make a restart to my simulator, zoom out in order to get a more general look at motion process, and then I will launch my program. So it's now making and building. Yeah, now it's connected. As you see here, this is port number and it's connected. So when we start our motion, wow, what we see here, we see new circles. This is our estimate. So what happens? What happens here? We got measurements from lidar and radar, and we use UKF in order to get these green dots. This is the estimate of our trajectory. Not only that, but here RMSE is calculated, root mean square error, and as we see, root mean square error has small values. This means that our filter converges and our estimates are reasonable. And here in or the results of the code is the estimated state vector with the estimated covariance matrix. And when we take the square root of the diagonal elements of this covariance matrix, we will see that they have values similar to or close to the values of root mean square error, and it means that my filter works well. So again, the code, the link to the code is in the description. Have a look at it. Thank you.